So we'll start with high frequency wave analyzer today. So this is the basic block diagram of a high frequency wave analyzer. You have the signal that's was passed on to the attenuator. It goes to the input amplifier. In this case, you'll be using a mixer. You have an amplifier. So this is the block diagram of a high frequency wave analyzer. If you compare it with an AM wave analyzer, in case of AM wave analyzer, we use actually an RC circuit, a tunable RC circuit filter that will help us. That's actually used as a heterodyne system in itself that will actually help us uh, change the frequency of your input waveform to the intermediate frequency level. Whereas in case of high frequency wave analyzer, instead of using an RC tuned filter, we use mixers, and it's the mixers uh, that actually add up two different signals to produce an intermediate frequency level. So in this case, what we do is that in this wave analyzer, the input amplitude modulated, that's a AM frequency waveform, and a radio frequency signal, they are actually combined together to produce another signal that will be at the intermediate frequency level. Uh, our filter will be already tuned to the intermediate frequency level, so it will only be passing through that frequency component that will then go on to the meter for measurement. So in this case, we use a mixer, and the job of the mixer is to mix two different signals at different frequency levels to produce another signal that will be at the same intermediate frequency level as that of the filter. Fine. So we can use two different mixers to do this. Now this mixing can be done using two methods. In case of a high frequency wave analyzer, we can simply we can either multiply the two frequencies. We can have a multiplication type. Right. So you are mixing the AM frequency with the RF frequency to produce another signal of frequency that will be at intermediate frequency, and our filter is already tuned to this intermediate frequency level so as to analyze that particular frequency component for measurement of its amplitude voltage extra. So now this mixing can either be, we can use a multiplication type mixer or we can use an addition type mixer. In case of multiplication type, the two signals are multiplied with each other. In case of addition type, the two signals will be uh, added up together. Say for example, in case of addition type, what we have is, say for example, the frequency produced by the oscillator will be V naught cos omega t, and you'll have another signal that will be coming, that will be in this case, uh, this is an example one. This will be the signal produced by the upper one is the signal produced by the oscillator, while the second signal is the local radio frequency signal that we are actually trying to analyze. Uh, so what the mixer will do is that it will combine the two signals V naught cos of omega t plus simply the addition. You can have the addition of these two, or you can have the multiplication of these two. In case of addition, you'll simply you'll get a signal like this. Now you can see this output signal that will come from the mixer will actually have while you when you add this up, you can see that this will have omega naught plus omega c component. This will have omega naught minus omega c component. This can have omega naught plus omega m minus plus minus omega c component. We can have omega naught minus omega m plus minus omega c components. So you can have you will this particular signal अगर आप इसका पूरा एडिशन करोगे the cos of a cos of b is equal to something cos of a plus b cos of sin of a minus b whatever. तो इसमें सारे फ्रीक्वेंसी कंपोनेंट्स होंगे इसमें ओमेगा नॉट प्लस ओमेगा सी ओमेगा नॉट माइनस ओमेगा सी ओमेगा नॉट प्लस ओमेगा एम माइनस प्लस माइनस ओमेगा सी so you'll have different you will have signals that will be comprising of different frequency components. Fine. Now this signal is getting passed on to the filter. Now our filter will be tuned to a particular frequency. It will be say for example tuned to omega naught plus omega c. So उस particular ये जो जब आप इस particular signal को add up करोगे when you will expand this cos of a cos of b plus then cos of a plus cos b plus another cos of omega t component यहाँ पे. Once you expand this, you will find a signal that will consist of all of these frequency components. Your filter then will be tuned to a particular frequency component only. That will be, say, for example, omega naught plus omega c. So your filter will only pass that signal, while as it will reject all other frequency component signals. So this is how this high frequency wave analyzer works. Using a mixer, you can produce you can produce a signal that will comprise of all frequency levels, but your filter will be tuned to a particular frequency level only. That will only allow that signal to pass through while as rejecting all other frequency components. So this is how an high frequency wave analyzer works. So next up we have measurement of harmonic distortion. So you know actually what harmonic distortion means. You have studied in power electronics also perhaps. You have a number of frequency components that will have their own amplitudes that will actually result that will actually cause ripples in the fundamental frequency component that are actually undesirable in the power system or in electronic circuitry as well. So we need to measure these harmonic distortions. So to do that, what we can do is we have actually three different methods for measurement of harmonic distortion. So all of these are actually only wave analyzer basic operation to same that you are actually trying to measure a particular frequency component, while as you are not dealing with any of the other uh, frequency components. So for measurement of जैसे हमने wave analyzers किया, we have AM wave analyzer and a high frequency wave analyzer. They are mostly used for radio frequencies, uh, for AM waves, for short waves, for megahertz of frequency waveforms. Now you have harmonic distortions. Now these harmonic measurement of harmonic distortion. So you can measure harmonics present in your power system, your currents, voltage, extra by these three different methods. One is the tunable selective circuit, another one is the heterodyne, and the third one is distortion measuring component. Basic operation is still same, that you are selecting only one frequency component while as rejecting all other frequency components. So there's nothing, the basic operation of all of these circuits is almost same. The circuitry is somewhat changed to accommodate for the frequencies and for the voltage levels extra. So in case of a tunable selective circuit, this is a basic block diagram. You have an input and attenuator, you have an amplifier, you have one simple amplifier, you have a tunable amplifier as well. This VTVM is simply a measurement meter that will help indicate us the distortion levels. Uh, so in this case, what we do is this wave that we need to analyze for harmonic distortions is first of all passed through the attenuator, and that's actually tuned to a particular frequency using a oscillator. That can be a crystal oscillator. From this attenuator, this goes to a selective amplifier circuit. This tunable amplifier circuit. इसकी property है that this tuned amplifier circuit will be tuned to a particular frequency component only. Fine. Your input, your wave is passed through an attenuator first, that's tuned to a particular frequency using the oscillator. जैसे मैंने आपको बताया attenuation की characteristics क्या होती है. It will have 100% power level for a particular signal while as rejecting all other uh, signals. Now we are using an oscillator. इसका मैं अभी reason बता दूंगा क्यों. From this attenuator, we are passing this on to an amplifier and then to a tunable amplifier. This tunable amplifier will be tuned to a particular frequency. तो इससे क्या होगा कि say for example आपका जो amplifier होगा that's tuned to 150 hertz. So you will only be able to measure the magnitude of the frequency components, that is 150 hertz. Fine. Only that frequency component will be passed on from the tuned amplifier while as rejecting all of the frequency components. So then this goes to the meter. ये जो meter यहाँ पे, this is a vacuum tube based voltmeter, VTVM. So that will give you the magnitude the of that particular frequency component. Fine. पहले इनपुट आपका एटेन्यूएटर को जाएगा, एटेन्यूएटर से एक selective amplifier को जाएगा. Amplifier will be tuned to a particular frequency. That means only one particular frequency component will be amplified and that will be passed on to the metering device while as rejecting all other frequency components. This is how you can measure the magnitude of one particular harmonic order. Say, for example, you want to measure the ninth harmonic, the 11th harmonic, or the fifth harmonic. You will tune your amplifier, you will tune your attenuator to that. You will make sure that your attenuator passes on only that signals around that particular frequency, and then your tuned amplifier will also make sure that only that particular frequency component is amplified while as rejecting all other frequency components. So this is how you measure one particular, you measure the magnitude of one particular frequency component uh, using this tunable selective circuit. Now, if you want to measure, if you want to get a uh, harmonic spectrum, you want to see the magnitude of all the harmonic components. That is the first, the third, the fifth, the seventh, the ninth. You want to see the magnitude of all of these different harmonic components present in your signal. So in that case, you set your oscillator of the attenuator to allow 100% of the fundamental frequency component. Once you do that, that will make sure that all of the frequency components will pass through proportional to the fundamental frequency component. We already know that all of the frequency components have some uh, they are a fraction of the fundamental frequency component. So using this, by tuning the attenuator to allow 100% of the fundamental frequency components, all the harmonic orders will be passed on as a ratio of the fundamental frequency component. So in this way, all the uh, you can actually have a number of harmonics as well as the fundamental frequency component passed on to the amplifier. And in this case, we actually make sure that the amplifier passes on all the frequency components. We can tune it in such a fashion to allow all the frequency components to pass through. And in this case, in that manner, we can get a harmonic spectrum instead of the magnitude of only one particular frequency component. So as I was saying, this tunable selective circuit can be used for measurement of both the magnitude of only one particular component or the magnitude of the entire harmonic spectrum. In case of if you want to measure the magnitude of only one particular frequency component, the attenuator is set first of all using the oscillator to that particular frequency component so that it allows only the frequency components around that, and then the tuned amplifier circuit, it's tuned to that particular frequency component so that only that particular frequency is allowed to pass through, so you can measure the magnitude of that particular frequency component. In the second case, in which you want to actually measure the magnitude of all the frequency components, what you do is you set the attenuator to allow 100% of the fundamental frequency. We know that all of the harmonics are actually a ratio of the fundamental frequency components, so all those harmonics will be allowed. Almost all of the significant harmonic components will be allowed. And then also the amplifier circuit is in that case set to a constant gain so that irrespective of whatever the frequency is passed through, it will be amplified. So using this method, we can actually measure the magnitude of the fundamental frequency as well as all the other all the lower order frequency components that are actually having a significant magnitude as compared to the higher frequency components.